We are pleased to have Euiwoong Lee from Michigan. We'll talk about Karger-Stein.
Right. Thanks a lot for the introduction. And then for inviting me and letting me give a talk. So it's always a pleasure to visit my EBS and this Discrete group and give a talk here. So yeah, today, as Sangil said, I'm going to talk about K-cut problem. And then actually, I thought about it, and it's my third time to give a talk on K-cut in this Discrete group. So yeah, I've thought about this problem for quite a while. But then I can promise that it's going to be like almost my last talk on this topic. And then it's almost the final result.
Almost no audience overlap.
Oh, okay. Okay, then yeah, it's the best version.
Almost the last, so you only will talk finitely many more times.
Yeah, exactly. So yeah, so the K-cut problem, I think it's a very fundamental and cute computational problem. So for this problem, the input is a graph G, so possibly edge-weighted. Though we're gonna assume in this talk that the edges are unweighted, so just like simple graph. And then we want, and then an integer k. So we are given like graph G and integer k, and then we want to delete the minimum number of edges to partition the graph into k connected components. Okay, so that's simple problem. And then we're going to think of k as like some constant, possibly large. So k is 2, 3, 4, things like that. Okay, so just to make sure, so this is one example for the instance. So this is a graph, and k is 3. And then this is one possible 3 cut. Because like if you delete all these like 4 dotted edges, then we're going to get 3 connected components. Okay, so this is the one possible 3 cut. And this is another one. So so we have 2 singleton components and then like 1 large component. Okay, so one interesting aspect about this problem is that I don't care the size of each component. Probably it's more natural to ask the size of components to be balanced, but then we don't put any restriction as long as they are non-empty. Okay, so like it's like k minus 1 singletons and then 1 large component is totally allowed. Okay, so yeah, so this is a problem. And then yeah, motivation. So I think for discrete math groups, I think it's a graph cut problem. And then it's pretty simple and fundamental 1, so I think that's enough for here. So and then just like to clarify the notation. So whenever I say k-cut, I will mean 2 things interchangeably. So the first thing is a partition of vertex set into k non-empty parts. And then secondly, I also will mean the set of edges crossing different parts, just like usual mathematical notion. But then whenever I say a size of a cut, I will always count the number of edges. Okay, so this is like 1, and then whenever I say cut without a number, then I will usually mean the 2 cut. Okay, so this is a cut, which is a partition of vertex set into 2 parts, and then also like the set of like 4 edges crossing different parts. Okay, so this is a notation. And then yeah, so this is a computational question. So one can definitely ask the following computational question. So given a graph with n vertices and a k, how fast can we compute the minimum k cut? Okay, so this is pretty standard algorithm problem. But then secondly, since it's discrete math group, so I prepared a special question saying given a graph with n vertices, so there may be like many k partitions that give the optimal k cut value. And then yeah, we're gonna study how many minimum k cuts are there if you're given a graph with n vertices. Okay, so we're gonna study 2 questions simultaneously, and then surprisingly, actually, the answer for both questions are closely related. Okay, so we're gonna study 2 questions, but then yeah, so let's first study the extremal question, which is simpler to think about. So yeah, let's get some lower bound. So I'm gonna look at the cycle with n vertices. Okay, then we know that if you want to partition a graph into k pieces, then we gotta delete k edges. So of this k, obviously. But then we can also see that any way of deleting k edges will give you like k components. Okay, so of this k and the number of k minimum k cuts is n choose k. Okay, so n choose k is a natural lower bound for this question. And then another like interesting example is a complete graph with n vertices. Okay, so so if you're given kn, and then suppose that k n is much larger than k, then can you guys guess what's gonna be the optimal k cut?
K minus 1 singleton.
Exactly. So yeah, you're exactly right. So optimum k cut arises by choosing k minus 1 singleton vertices and then deleting every edges incident on them. So if you do this, then you can see that the opt is when n is much larger than k, then it's essentially n times k minus 1. And then the number of minimum k cuts here is exactly the number of ways to choose a k minus 1 vertices, which is like n choose k minus 1. Okay, so for both examples, n choose k or n choose k minus 1 are like natural lower bounds for like these two specific graphs. So yeah, so n to the k sounds like the right ballpark if you want to study extremal question. And then even for the computational question, so I'm not gonna tell you exact reduction, but then inspired by somehow this connection between a click and k-cut, one can show a reduction from computing some version of a k minus 1 click to a minimum k-cut problem. So if you assume some kind of bold complexity conjecture, then one can say that, oh, n to the k minus 1 is a natural time lower bound for even a computational question. Okay, good. So then, yeah, n to the k is a lower bound for the extremal question, n to the k minus 1 is on the lower bound for the computational question. Now, of course, we gotta study upper bounds. So upper bounds. So then, yeah, let's try to give an algorithm for this problem. When k is 2, which is known as a global mincut, then at least like there's like one naive strategy to get a polynomial time algorithm. Because like what we can do is that we can guess like two terms, s and t, which are in different parts in the optimal 2 cut, and then try to solve the minimum cut separating s and t. So this is a SD cut problem which can be solved in polynomial time using maximum mincut theorem. So at least when k is 2, there is a simple polynomial time algorithm by reducing the problem to SD cut. But then the same strategy is not going to work when k is even 3, because like the natural analog will be to guess like 3 terminals, s, t, and w, and then I'm trying to find the minimum cut separating those 2 terminals from each other. But then this like terminal version is known as a multi-way cut. And then this problem is NPR even when k is exactly 3. Okay, so we gotta find a different strategy to solve a take-up problem even when k is 3. So that's why it took some more time for people to find the polynomial time algorithm even for like a fixed k. So this was first done by Goldschmidt and Hochbaum in '88. So their running times n to the k square. And then Karger and Stein gave this like beautiful algorithm that we're going to study. And then their algorithm runs in time n to the 2k minus 2. And then so I said enumeration here because not only it finds you a minimum k cut, actually in the essentially the same running time up to like log factors. So it's gonna give you all the minimum k cut in the graph in this running time, which also answers the extremal question, because then this running time gives you an upper bound on the number of the k cuts in the graph with n vertices. Okay, so we're gonna go back to this algorithm because like this is actually our paper is about. And then so this algorithm was randomized, but then the deterministic algorithm with essentially the same guarantee was discovered later. And then so as I said, I've thought about this problem for 3 years, so we got some preliminary results. But then our like main theorem today is essentially resolving this question, saying that just take this algorithm, and then they proved that this algorithm runs in time n to the 2k minus 2. But then we actually showed that the same algorithm runs faster than what they proved. So we proved that there is a randomized algorithm that finds all minimum k cuts in time n to the k. Okay, so and then as I said, then actually it gives the extremal bound as well.
Is there independent proof of the extremal bound?
No, that's the only proof that we know. Yeah. So actually, that's a open question to get the exact number.
But you have to kill that in low factor.
Okay. So I think there's 2 versions. So I think so the first version has like the log n factors and things like that. But then like in the final version, we removed everything. So it's now it's almost it's only a constant depending on k. So there's no tilde. Yeah, this is a typo. Okay, so this is the result. And then before we begin, so the k-cut problem, there are like at least like 2 natural parameters, n and k. So there are like many time regimes that one can think about. So for example, if you want the algorithms that run in purely polynomial time, polynomial in both n and k, then also there's like a very simple two approximation algorithm discovered in 1995. And then if you assume some other like complexity conjecture, then in purely polynomial time, there's like 2 approximations optimal. And then another interesting time regime is like the parameterize time regime, where we want the algorithm that runs in time f of opt. So opt means the number of edges in the minimum k-cut. So f can be any function, and f of opt times like polynomial n. So this there's a paper by Karger and Thorup that solves the problem exactly in this running time. And then so another like regime I talked about was this f of k times the polynomial in n. Okay, so k is the number of parts. So in this running time regime, so it's known that it is W1 hard. So it's unlikely to be able to solve the problem exactly in this running time. But then, so 3 years ago, so we gave a 1.9997 approximation algorithm, showing that we can do slightly better than this time regime. But then people worked on it quite quickly, and then now one can get the 1 plus epsilon approximation algorithm in time polynomial in n times like some function of k and epsilon. Okay, so now even for this time regime, I think the complexity is almost resolved. Okay, so yeah, so these are results for the other regimes. But then yeah, let's go back to our like usual setting and then study Karger-Stein algorithm. Okay, so at least like in the computer science like education or literature, so the Karger-Stein algorithm is kind of at least when case 2. When we are solving mincut, this is the example randomized algorithm. So when you teach a course in randomized algorithm or when you took it, then I think this like is almost always the first algorithm that you teach or learn. So this is the first algorithm on the textbook on the left. It's a third algorithm on the textbook on the right, and so on. Due to its simplicity, elegance, and then perhaps nice consequences to mathematics. Good. So then, actually, yeah. So let me check. So how many of you have seen the algorithm? I'm gonna one. Okay. So yeah. So feel free to stop me at any point. So yeah. Okay. So yeah. Let me describe the algorithm. You see, algorithm is extremely simple. Okay, so it's a kind of iterative algorithm. And then what we do is the following. So we start from the original graph. And then in each iteration, we pick a random edge uniformly, and then just contract it. So when you contract an edge, then number of vertices decrease by exactly 1. And then the process of contracting an edge may create self-loops and parallel edges. So we keep all the parallel edges, but then we delete self-loops. And then we just like iterate this process until we have a k vertices. Then yeah, when we have a k vertices, then each vertex in the final graph will correspond to some subset of vertices in the original graph. So that k vertex, the final graph will correspond to k cut in the original graph, and that's your like answer basically. So just to make sure, so this is one example of how the algorithm works. So suppose that this is the original graph, and say k is 2. So we choose a random edge and contract it, and we choose another edge randomly and contract it. And then another edge, contract it, and so on, until we have exactly 2 vertices. And then yeah, when we have 2 vertices, in this run, miraculously all the red vertices were contracted into one red vertex, and all the white vertices were contracted to this vertex. And then this like the 3 edge cut is a cut you output. And then again, like in this example, miraculously the algorithm was right. So it gives you like minimum 2 cut. But then of course, like yeah, it's a randomized algorithm, so with like large probability, it's gonna fail. But then the main theorem, actually, we're gonna actually prove is this like following theorem, saying that if you just look at this like the one run of Karger-Stein algorithm, then if you fix any minimum k cut c in the beginning, then the probability that this algorithm will output exactly this cut c is at least 1 over n to the k. Okay, so this is actually the theorem we're going to prove. And then yeah, one can see that if you get this, then you actually you get both the extremal question and then algorithmic question as a consequences. Because like if you want to see the extremal question, then yeah, we can just simply say that like probabilities must sum to at most 1. So the number of different minimum k cuts should be at most reciprocal of this number, which is n to the k. And then for the algorithm question, what we can do is just run the Karger-Stein algorithm n to the k times first like log n times. Then with high probability, we are guaranteed to see every minimum k cut at least once. Okay, so yeah, so this is the algorithm and then the statement we're going to prove. Is there any question about the algorithm? Everything's clear? Good. Then let me present this original analysis by Karger and Stein, which gives us n to the minus 2 k minus 1. So I think notice that actually when k is 2, then this their analysis is exactly tight, and then we don't prove anything new. I mean actually their analysis is exactly tight, so there's nothing to improve. But then so that proof is just one page. It's like 3 more lines from here. So in order to do their analysis, then what we're gonna see is that let's fix like our minimum k cut c. Then we know that so the algorithm will output this like a fixed cut c if and only no edge of the cut c is contracted during the algorithm. I think this is kind of easy to see, but then yes, because like if you contract an edge of c during the algorithm, then there's like no way that the algorithm will output c. And then if no edge of c is contracted, then when you have a final graph, then exactly the k-cuts will be exactly c. Okay, so with this observation, then all we need to do is to analyze the probability that some edge of c is contracted during the algorithm. Then let's look at one iteration when we have r vertices. Okay, then what's the probability that we screw up? What's the probability that we construct an edge in c? So that's simply the number of edges in c, which is like out, divided by the number of edges in the current graph. And then I want the upper bound, there's like numerator out. Okay, so opt is like on the value of the optimal k-cut. So the one way to give an upper bound is just present you arbitrarily k-cut in the remaining graph. And then the way I will do it is to, again, as the assignment said, so I'm gonna take k minus 1 vertices of the smallest degrees, and then remove all the edges incident on that. So that's a feasible k-cut. So its value must be at least the opt. And so one can say the opt is at most the sum of the smallest k minus 1 degrees. And then of course like number of edges is r times average degree of the current graph divided by 2. So then one can see that the average of k minus 1 degrees is at most the average degree itself. So then one can easily give an upper bound of 2 times k minus 1 divided by r. Okay, so that's a failure probability for one iteration. Then all we need to do is to, so the overall success probability is a product of 1 minus failure probability. So we're gonna get this gigantic product terms. And then at this point, there's like many ways to analyze it. So you can just approximate 1 minus x by e to the minus x, or you can, if you just look at this n terms, then there will be like massive cancellations between numerators and denominators. So in any way, so it's gonna give us n to the minus 2 k minus 1. So when k is 2, it's gonna give you exactly n choose 2, 1 over n choose 2, and then this is exactly tight because if you look at the cycle cut, and then it has like exactly n choose 2 min cuts. I think this is the kind of most important side of this talk, so let me just pause for 20 seconds.
So the reason why you can make a product of these numbers, these probabilities, because all the events are independent.
Yes.
So is the cut C minimum weight k-cut or cardinality-wise optimal k-cut?
Oh yeah, so yes. So it's gonna be like minimum weight, but then in this talk, we're gonna assume that graphs are unweighted. So
It works for weighted.
Yeah, it works for weighted. Yeah. So then the opt becomes the weight, the denominator becomes weights. Yeah, everything works just fine.
So if you consider weighted version, the first inequality doesn't hold, right?
First inequality? No, I think it holds because it's gonna be the sum of weights of the k minus 1 degrees. I mean, and then just like convert degree to weighted degree. Yeah, so that's this is why this is kind of the example of randomized algorithm. You can teach in one lecture in any course. So so that's the analysis.
Or say k equals 3, which inequality?
I think okay, so what is not tight? I mean, yeah, it's I think yeah. So I think yeah. So the upshot is like this upper bound is will be kind of loose. Actually, I mean, this is exactly the next slide. So let's let me try to address it. So then yeah, but then yeah, as you pointed out, so then one can see like where the culprit for this the factor 2 loss is. Then of course one can see that yeah the culprit is here, where we upper bounded this like ratio between opt and number of edges by 2k minus 1 divided by r. For example, if this thing becomes a k over r, then we exactly get n to the k that we want. So then like our job is to see like whether this this upper bound can be tightened. Okay, so then yeah, let's go back to like the previous two examples. Okay, so the first example, cycle with r vertices. It's a perfect because like opt is k, number of edges are, so it's a k over r. So so it's exactly tight. But then it breaks down for like complete graph with r vertices, because as Sanya said, the opt is basically k minus 1 times r, and the number of edges is the r choose 2, basically like r squared divided by 2. So if you look at the ratio between number of edges and opt, it's going to be like this like naive upper bound 2k minus 1 divided by r. Okay, so yeah, this is bad. So yeah, so we cannot hope to improve this like the naive upper bound for every graph. But then yeah, we don't need to give up, because like it's a kind of the randomizer process where like the graphs is shrinking. And then yeah, so even when we start from the complete graph with r vertices, so we are like changing graph randomly, and then there's no way that actually this analysis is tight for every iteration. So if you start from complete graph with r vertices and then just run the process, say like r over 2 times, then I just computed something here. You don't need to follow it, but then I think because like the process like contracts many edges, that's gonna create like many parallel edges. So that's gonna increase the denominator here. And then yeah, so here I just wrote down that, so however you contract the outer over 2 edges, starting from the complete graph, this ratio between opt and number of edges cannot be tight. Yeah, so the main intuition is that yes. So in one iteration, this like the stupid upper bound can be tight, but then it will not be tight in every iteration. So we can still hope to do better. Okay, so this is like one simple intuition, and then let me see how we formalize this thing. Yeah, so this is the outline of the proof. Okay, so this is the theorem, same one we want to prove. And then let me just like define one notation. Lambda k bar is opt divided by k, because like we're gonna compare the size of cut to lambda k bar. So it's a normalized value of opt. So the proof is divided into 2 parts. So first, let me define the small cuts to be the cuts whose size, number of edges, to be at most 2 minus epsilon times lambda k bar. So epsilon is some constant greater than 0. Then like second part, we're going to show that if you look at any graph with n vertices, the number of small cuts whose size is 2 minus epsilon times lambda k bar is at most like n linear in n times like some function of k and epsilon. Okay, so that's the purely the extremal statement. And then given the second part, we kind of use it to show that if this is true, which is true, then actually the Karger-Stein analysis can be better than what they did. Okay, so this is the outline, and then let me first present the first part. Okay, so to present the first part, let me slightly change the viewpoint, which is like more continuous. We'll look at the like same like random graph process. Okay, so in this like process, so time flows from 0 to infinity continuously, and then each edge has an exponential plot with rate of whatever lambda k bar. Okay, so at least for me, so the slightly more discrete way to think about it is that the entire time is a partition into intervals of length delta, and then in each interval time step of length delta. So each edge wakes up or like fires independently with probability delta over lambda k bar, and then like when an edge fires, then we just like contract the edge in the usual sense. Okay, so for example, so time flows from 0 to infinity, and then for E3 wakes up first, so we contract it, and then E5 fires. So we contract E5 if it still exists in the graph, and so on. Okay. So this is again like another like random graph process. But then yeah, one can notice that so then like we gave like 2 random processes. So first one given by just a description of the algorithm, and the second one given by this continuous process. But then one can see that the way the graph evolves is exactly the same in both processes. In both processes, the way that graph is shrinking is that we just like simply take a random order over entire edges, and then scan the edges one by one in this order, and then just contract it. Okay, so yeah, so I just gave a new process, but it's the same thing as before. But then this like viewpoint at least like give us some conceptual advantage because like almost everything is independent here. Okay, so yeah, so under like this viewpoint, then what you want to prove is that for some time t, if you fix some time t, then the resulting graph at time t is some random graph, and then we want to prove that at this time t, the probability that the number of vertices becomes constant depending only on k, and then our like fixed minimum k survives is at least n to the minus k. Because if that is true, if that event holds, then then the probability that the final graph with k vertices will be our k cut is like some function of k, which we can ignore. Okay, so yeah, if that's true, then our minimum k cut will be output with probably n to the minus k. So this is what you are shooting for now. Okay, so let's try to prove this. But then in order to like analyze this process, so first we will look at how fast the number of vertices will shrink. Okay, again, let's look at the one point of the time when we have r vertices in the current graph. By essentially using the previous analysis, then we can assume that there are at least r times the lambda k bar divided by 2 edges in the graph. So here I'm gonna like actually gloss over the difference between k and k minus 1, which means that because like if you look at one time step, then each edge will be contracted with probability delta divided by lambda k bar. So then in expectation, we're gonna contract at least the probability times the number of edges, which is r delta divided by 2 edges in expectation. Okay, so that's what will happen in one time step. So we're gonna contract that many edges in expectation. So the number of vertices will decrease also by r delta divided by 2 in one time step, which is like the delta over 2 fraction of the entire number of vertices. So it's kind of informal, but then one can say that after time t, then the expected number of vertices is original number of vertices n times the rate of decrease in each time step, 1 over delta over 2, raised to the number of time steps, t over delta. And then of course, like if you let delta to go to 0, then it's going to be n times the e to the minus 2 over 2. Okay, so this is kind of the upper bound, one upper bound on the number of vertices in this like process. Okay, so so this this is decent, this is good, and then we can do something with it. So then it means that then if you run this process, perhaps like until like on time 2 log n, then the expected number of vertices will become 1. Because like and e to the minus t over 2 will be like e to the minus log n, which is like 1 over n. And then if you look at the time 2 log n, then the probability that our fixed minimum k cut survives is a probability that like one edge survives in one time step, which is like 1 minus delta over lambda k bar, raised to the power of the number of edges times the number of time steps, which is like k lambda k bar times the t over delta. So if you run the process for like 2 log n times, then the probability that our minimum k cut survive is e to the minus k t, which is exactly n to the minus 2k. And then this then we essentially rediscovered the Karger-Stein analysis up to the difference between k and k minus 1. Okay, so so we proved that at time 2 log n, so number of vertices at most like constant, and then our minimum k cut will survive with probably at least n to the minus 2k. Okay, so this is kind of the rediscovery of the Karger-Stein analysis. But then of course like we want to do better. And then if you want to do better, then we gotta use the fact that we're gonna prove in the second part, which is that there are like only linearly many small cuts in the graph. Okay, so here I define the small cuts to be the cut whose size is between lambda k bar and then 2 minus epsilon times lambda k bar. I mean, there may be cuts smaller than lambda k bar, but then if you look at the fact 4, so there are like very tiny number of them. So we can, for this talk, we can just we'll assume that there's no cut of size less than lambda k bar. So yeah, so we assume that there are only like linearly many small cuts. But then if you fix one small cut, then the probability, if you look at the time t, then the probability that the one small cut survives at time t, if you do the same calculation as before, then it's going to be like, 1 minus the delta over lambda k bar raised to the power of lambda k bar times like t over delta, which is like e to the minus t, just like the way that we analyze the probability our k cut survives. Okay, so so this probably becomes e to the minus t. So then, if you look at the time log n, then there were like n of them to begin with, and then at time t, each one survives with probably e to the minus t. So at time log n, so the expected number of small cuts remaining is like 1, or like some constant. So we can essentially ignore that there are like no small cuts after time log n. Okay, so everything is expectation, but then that's kind of the intuition here. So with that fact, then let me give you slightly suboptimal, but then like slightly better than Karger-Stein bound. Okay, so we gather the facts that we're gonna use here. Then we're gonna use the same process, continuous process. But then what I'm gonna do is that I'm gonna divide the time into like 2 phases. Okay, the first phase is between like time 0 and log n. So here, for the number of vertices, I will use this like naive bound, the fact 1 that we derived, just like using the trivial analysis. So if you just like look at the fact 1, then we know that at time log n, the expected number of vertices will be root n. But then by fact 3, the fact we saw from the last slide, we saw that the number of small cuts will be like constant, or like they don't exist anymore. Okay, so that's the phase 1. But then phase 2, I think the magic will happen. So phase 2 is shorter, it's between time log n and 1.5 times log n. Then now we are assuming that there's no small cut left in the graph, which means that if you look at the current graph, and then like look at each degree, then previously we just like said that each degree is at least like lambda k bar divided by 2. But then now one can say that lambda k bar. But then now one can say that each degree is at least 2 minus epsilon times lambda k bar, because like there's no small cut remaining in the graph. So then with this like degree bound, then number of edges is a factor 2 more than what we used before, which implies that the rate of decrease in the number of vertices will be like twice faster in the exponent. Okay, so number of vertices will decay like root n times e to the minus t instead of e to the minus t over 2. So then after like only like half log n time, so number of vertices will be shrinked to a constant. And then if you look at the time 1.5 log n, then probability that our minimum k cut survives is n to the minus 1.5 k. Okay, so this is a kind of like rough intuition of how we can get n to the minus 1.5 k bound, which is not optimal, but then still like better than Karger-Stein. So so this is kind of the style of the analysis. Okay, so this is the first part. Of course, I guess to get all the way down to n to the minus k, then we just like set up differential equation, tracking the expected number of the remaining vertices and small cuts. Of course, like these two quantities depend on each other, so we set up a differential equation and solved it, and then it magically predicted that n to the minus k is a right answer. But then another issue is that everything I said, there's the number of vertices, number of small cuts, they all hold only in expectation. So at the end, we have to use like some standard concentric measure arguments to prove that everything holds with high probability. Okay, so so this is the first part, just like giving a better analysis for Karger and Stein. So any question about the first part?
So what is the randomized button?
Yes.
Know how to de-randomize.
Yes, that's an open question. Yes. So the first part. Then we're gonna we're gonna do like more fun part, especially for this group. So yeah, we're gonna prove this like extremal form, saying that if you define the minimum small cuts in this way, then the number of small cuts is like this much. Okay, so and then yeah, so before we do this, let me again do some sanity check. So this is a statement we're gonna prove. Okay, like again the sanity checks. So if you look at the cycle with n vertices, then for any k, lambda k bar is 1. And then so if as long as epsilon is like strictly greater than 0, this bound is trivially true, because like every cut has at least 2 edges. So if epsilon is greater than 0, then there's no cut whose size at most like 2 max epsilon times lambda k bar. Okay, so but then when you set epsilon to be 0, when you allow like 2 times lambda k bar, then out of sudden like all this n choose 2 the cuts qualify. So we are not expecting linear bound.
For many cuts of size and most twice lambda, something like that. But lambda wasn't lambda the opt divided by
K, yeah.
k. So k. I see. So if the k is 2, this.
Yeah, k is 2. Yeah, I mean, yeah, for any k, for a cycle, lambda k bar is 1.
Yeah, what's confusing to me is there k is big, then
Yeah.
this is like you're trying to find the cut of a small value. I see. So small cut.
Yeah, small cuts. Yeah.
I see. Okay.
No,
You're not counting k cut, right?
this is just cuts. This is just cuts. Yes. But then definition of lambda k bar depends on k.
Okay.
And then bounds depend on k as well. Okay, so yeah, so that's so theorem is tight in that regard. But then like similar things going on for clique as well. So if you so here like when k is smaller than n, then one can essentially say that lambda k bar is n minus 1, the degree of each vertex. So so if epsilon is like constant greater than 0, then if you look at the definition of small cut, then only like singleton cuts will qualify. So there are only n of them. But then again, if you let epsilon to be 0, then all the like doubleton cuts will qualify as well. So the number, we're not expecting the quadratic linear bounds. Okay, so yeah, so this is this is theorem. I think this is kind of like tight in these 2 examples, and then let's try to prove this statement. Okay. Yeah, so the way we will prove this statement is like simple. So yeah, we're gonna view this like the collection of the cuts as a like collection of as a set system. So simply what we're gonna do is that if you have a small cut that separates an A and A complement, then I'm gonna put A and A bar to our collection F. So then it's gonna be symmetric, which means that if A is in F, then A bar is in F. And then we're gonna use the fact that all these sets in our set system F are coming from small cuts, and then this fact will force F not to have like some substructures. So we're gonna see like 2 forbidden substructures, and then we will use like this the forbidden substructures to show that the number of sets in F is bounded linearly in F. Okay, so this is the structure of the proof, and let's try to see like what these like structures are. Okay, so the first structure is about like Venn diagram. I mean, everything's about Venn diagram. It's a set system. So so suppose that we take on k over 2 sets from our like set system F, which correspond to k over 2 small cuts. Then we take on k over 2 sets, so we can like draw like Venn diagram, and then I'm gonna count the number of occupied regions or like non-empty regions. Okay, so in this example, so there are we draw like 4 sets, and then there are like 8 non-empty regions coded by each color. 1, 2, sorry, so that's, but you know what. So 8 non-empty regions. But then suppose that we take k over 2 sets and then draw like Venn diagram. But then suddenly there are like at least like k non-empty regions. Then we're gonna reach our conjugation, because like then what we can say is that okay, then imagine the set of edges that corresponds to any of these like k over 2 cuts. So if you delete all these edges crossing the k over 2 cuts, then we're gonna separate each occupied region from one another. And then, but then, yeah, if we assume that there are at least like k occupied regions, then it already partitions the graph into at least like k connecting points. So, yeah, so which is like it's a valid k cut. But then if you count how many edges we deleted, then we only deleted k over 2 small cuts. But then each small cut is just slightly less than lambda k bar. So then, yeah, the number of edges we deleted is like k over 2 times like 2 minus epsilon times lambda k bar, which is like strictly less than k lambda k bar, which is out. So which is a contradiction. Okay, so the option. So this is like our like first forbidden structure. So we can say that if you take any of our k over 2 sets from our family, and then draw like Venn diagram, then the number of non-empty regions must be strictly less than k. Okay, so this is the first part. And then the second part, it has something to do with this like sunflower. Okay, sunflower is like this again the collection of sets where like each pairwise intersection is the same. Okay, so there's like 5 sets for a sunflower where like for each pair of sets, their intersection is exactly this like 2 red vertices in the middle. Okay, so this like 2 red vertices are called the pole, and then for each set, set minus 4 is called the petal. So like this like sunflower, I think has been like useful object in both combinatorics and then complexity theory. And then famous lemma by Algorithmic, which was kind of improved the last year as well, shows that if you have a set system where every set has like size at most d, so set has a bounded size, and then if you have some function of d and r sets, then you're gonna have a sunflower with r petals. Okay, this is a famous lemma by Algorithmic. And then I think so for them, the definition of sunflower allows like empty intersections. So just like pairwise the disjoint sets qualify the sunflower. But then for us, like we need a non-empty core. But then just like we can just like use this lemma as a black box, or like the last year's theorem as a black box, to show that if your set system has a size at most d for each set, and then if you have at least like n times like some function of d and r sets, then you're gonna have a sunflower with r petals and non-empty core. Okay, so this is the basic corollary that we're gonna use. But then, yeah, if you go back to our set system, then you can also conclude that our set system shouldn't have the sunflower, large sunflower, with non-empty core. Okay, so let's try to see why this is the case. So again, as I said, yeah, let's assume that every cut has a size at least lambda k bar. So that's our assumption. And then let's look at the one set participating in a sunflower. Okay, so this part, the red part is core, and then the blue part is the petal. But then anyway, so like both are non-empty. So if you look at the boundary of each part, the red part and the blue part, then their like boundary size is at least lambda k bar because of that because of the assumption. But then if you combine these two sets, then we know that like the whole set is coming from a small cut. So its boundary is like slightly less than 2 times lambda k bar, which means that there is some non-trivial number of edges going between these two sets, the core and the petal. Okay, so this is an easy consequence. But then if you have a sunflower with a large number of petals, then yeah, we have this like yellow strips. So yellow strips represent edges between core and each petal. And then yeah, we know that each yellow strip represents at least the lambda times lambda k bar edges. So if you have like too many petals, and then if you look at the first set again, then each of these yellow strips represent the different edges, but then they are all crossing the first set. And then yeah, each yellow strip like represents at least like epsilon times lambda k bar edges. So if you have many petals, say like 5 over epsilon petals, then it again contradicts the fact that like the first set is coming from a small cut, because the boundary for a set that becomes too large. Okay, so yeah, so this is a reason why we cannot expect a sunflower with non-empty core and then large number of petals. So yeah, with that sunflower lemma in our hands, then yeah, we could say that if the sets in our set system were like small sets, in this case in terms of number of vertices, then we could just like apply the sunflower lemma, and then be done, because like sunflower lemma guarantees that the number of sets should be at most n times some function of the R and D. Okay, but then yeah, for us like the challenge is that if you look at the sets in our the family, then each set is a number of, is a set of vertices, so we don't have a like bound for that. Okay, so that's a challenge. But then we also had the first forbidden substructure. So the theorem we're going to prove is that if you have a set system, or like a symmetric set system, where it doesn't have any of these like two forbidden structures, then the number of sets in F should be n times like some function over K and so on. Okay, so that's a final lemma that we're going to prove. Okay, so so this is kind of like quick induction as well. So so the base case is when all sets are like extremely small or like extremely large. So yeah, in this case, because we assume that the set system is symmetric, then we can just like use a sunflower lemma and then be done with it. So then we can assume that there exists a set with intermediate size. So suppose that there is a S1 in our set system whose size is strictly between 5k and then n minus 5k. Then yeah, starting from S1, so we're gonna do this the process. Okay, so for I from 2 until like k over 2, we're gonna add like S2, S3, S4. But then the way we add like set Si is only if when adding Si increases the number of non-empty regions in this like Venn diagram by at least 2. Okay, so for example, yeah, we started from S1 and then we added S2, S3, S4 here. So we added 4 sets and then we got the 8 non-empty regions in this Venn diagram. Okay, so this is how we added sets. But then since we look at since we have this like first forbidden substructure, so we know that no k over 2 sets should give you at least like k non-empty regions in the Venn diagram. So this process must stop strictly before k over 2. Okay, so that's so that's guaranteed. Yeah, but then after like stopping, let's look at the remaining sets in our like set system F. Okay, so yeah, some sets some sets may look like this, just a gray set. But then what we can say is that every set cuts one region, at most one region. So I say like set cuts a region if it intersects a region but not exactly contain it. Because like simply because like if one set contains like 2 regions, then adding the set into our collection will increase the number of regions by at least 2. But then we stopped. So every set cuts at most one region in this like current Venn diagram. So and then it's at most one region. So this must be a region inside S1 or outside S1. So yeah, so this set cuts outermost region, which is outside S1. And then, for example, this set may exist, and then this set cuts a region inside this region. Okay, so yeah, so we can classify all the sets into like 2 categories, and then like from this classification, we're gonna construct 2 new set systems. We're gonna construct 2 new set systems. The first set system contains like all the sets cutting inner region. Okay, so sets like this, cutting inner region. And then on top of this, what I'm gonna do is that I'm gonna contract each outer region to an element. Okay, so this is the first set system. So if you do this, then if you look at the number of elements in the first set system, then so n1 is at most the number of elements in S1 because like we didn't do anything for them, plus the number of outer regions out of S1. So, and then since like we assume that the size of S1 is intermediate, is less than n minus 5k or something. So we know that n1 is strictly less than n. And then the second set system is constructed in a somehow symmetric way. Okay, so it contains all the sets cutting outer region. So for example, like this set, cutting the outermost region. And then we're going to contract each inner region to an element. Again, then the number of vertices in the second set system will be strictly less than n. And then you may wonder, like, there may be sets that don't cut any region. Then in that case, actually, you can put this like set into any of the set systems, perhaps even both. Okay, so that's how we construct two new set systems. But then, yeah, one crucial observation is that if the original set system doesn't have the structure 1 and 2, then neither will the two new set systems that we constructed. So I mean, formally, this is very easy to check. So, and then one intuitive reason is that so if you if you look at two set systems that is created, then the only reason that it may have a new forbidden substructure is simply because we kind of contracted a region to an element. Because if you contract generally, if you contract some elements into one element, then some sets that didn't intersect before may intersect. But then, since because of the reason, because of the way we constructed the success system, so whenever we contracted a region to an element, then we made sure that each subset in the new set system either entirely contains it or it's completely disjoint from it. So yeah, so the contracting region to an element is not going to increase some complexity of the set system. So this is kind of intuitive reason that why these two new set systems will not have any of the forbidden structure. Yeah, it's easy to formally verify. But then if you believe 1 and 2, and then we can just use the induction hypothesis because n1 and n2 are strictly less than n. So this gives us this following recurrence relation, and then if you solve it, then it's going to give us this bound. Okay, so that's the whole proof for the second part, almost whole proof. So that's done. Yeah, so again, this is the statement we proved, and then so the proof was divided into two parts, and then we proved each part kind of separately. Okay, so so this was a theorem, and then and then this is kind of the theorem I wanted to prove for a long time, but then there are still open questions. So so the first question, so we basically gave an upper, so extremal, for the extremal question, so we gave an upper bound of n to the k times some function of k, upper bound. But then, of course, the best lower bound is n choose 3, n choose k, coming from the cycle. So the open question is can you exactly get this the upper bound n choose k? I mean, obviously I think it should be true, and then it is true when k is 2. But then even when k is 3, there's a constant gap between upper and lower bounds.
You said it's actually you got n to the plus little over 1, but do you actually have O n to the k here?
So I think our final result is so n to the k times some function of k is our upper bound. Yes. Yeah. So this is an extremal question, and then second question is of course related to what Sanil asked. So it's kind of the prime example of randomized algorithm. But then whenever you see a randomized algorithm, then you want to de-randomize it. So can you get a deterministic algorithm that matches n to the k bound? I think if you are looking at this general weighted graphs, then n to the 2k is the best one in time. And then so third question I think hinges on this sort of distinction between weighted graphs and then unweighted graphs, because every algorithm I said works for the weighted graphs. But then if you look at the unweighted graphs, then this the time lower bound of n to the k minus 1 doesn't hold. And then actually, and then the time lower bound is this the funny number which is n to the k omega divided by 3, where omega is a matrix multiplication constant, which is currently 2.3 something. So just because some the unweighted k clique has an algorithm that runs in time n to the k omega divided by 3. So this is the best time lower bound for unweighted graphs, and then it may have the faster algorithm that matches this time lower bound for unweighted graphs, unweighted simple graphs. So that's it. All right, thanks.
Was the known upper bound for weighted case? For deterministic weighted case?
N to the 2k I think is still the best.
So n to the 2k is by Karger-Stein, or is
Yeah, it's by Thorup. I mean, to me, it looks like completely different. So because like what they proved is that they proved that by tree picking algorithm. So they proved that there's a polynomial time that produces like a collection of like polynomial many trees, such that there exists for every minimum k cut, there exists a tree in your collection that is cut at most like 2k times. So if you have this guarantee, then yeah, you can go over your tree and then just like cut 2k edges, and then reassemble to get k components. And then in that way, every minimum k cut will be enumerated.
And what's known as a weighted multi-result? So when you guess these k terminals?
Oh yeah, then I think it's NPR, and then even when k is 3, even for general k, there's like 1.3 approximation, 1.29 approximation is kind of like famous problem in approximation algorithms. And then for lower bounds, I think for general k, if you assume unique gains, then you can't do better than 1.2, something like that. And then when k is 3, I think that the exact approximation constant is settled down. It's like 7/6%.
There's a question from the live chat. Do you also get improved results for the number of k-cuts that are within a constant factor of optimum?
Yes, I think so. Yeah, so I generally I forgot to say that actually. Just if you look at the Karger-Stein analysis, when k is 2, and then if you look at some number alpha greater than 0, and then if you look at the number of alpha approximate mincut, then the Karger-Stein bounds you give you the n to the 2 alpha bound for alpha approximate mincuts. And then I think, so I think the similar statement will work for the k-cut as well. There's nothing really changing, though we haven't written down.
Is there a matroid version as well? Like you can contract on elements in matroid and.
Yes. Okay. So at least for the hypergraph version, I think people recently started to look at it again. So there's the Karger-Stein algorithm. I think n to the 2k I think was reproved by n to the 2k bound holds for the hypergraph version. But I'm not sure like n to the k is easily extendable or not. I haven't thought about it. And then I think getting deterministic algorithm for any like running time for fixed k was like kind of like open problem because like this like tree picking approach didn't work. But then it was kind of resolved like recently, last year or something. And then I think people are one way I think people are trying to generalize is kind of some modular partitioning. So you're given some modular function, then you wanna find the k partition that minimizes some of the modular function values. So this is one result I think one research action that's selective.
K equals 2, so you're just solving the mincut and apply the Karger-Stein.
Yeah.
So can you get a deterministic algorithm that matches the running time?
Yeah. So I think okay. Let's see. So when k is equal to 2, then you gotta worry about this extra n terms and m terms. I think so. Okay, good. So Karger-Stein, because I given it, so naively, the success probability is n choose 2. But then running just one run of Karger-Stein takes you like polynomial times. So if you're just doing naively, then it's gonna be like probability bound times like some factor. But then I think there's like some slick trick to avoid this. So one can essentially get this Karger-Stein result, enumerating all the minimum k-cuts in essentially the same running time, losing only log n factor. So deterministically, can we enumerate all the min cuts in n squared time? I don't think it's known. I think perhaps you gotta pay another factor n or something. So but then if you switch to just like finding one minimum cut, then I think Karger's different algorithm, totally different algorithm. Gave a randomized algorithm that runs in essentially order m time. And then the randomizing it was an open question, which was resulted in this theory stock. The one minimum one min cut I think it's a de-randomized. Any other questions?
If not,